Ah, welcome. We are but 4 class periods away from being done together. Obviously, there's so much more that we could do if we were in school, but as the last little bit that I want us to learn together this year, I want us to kind of combine some of the concepts of momentum and energy um, into some really powerful physics equations. And I'm going to kind of show you some things in the coming days about that, and we're going to do some work on that. Obviously, I know momentum was not a lot of people's favorite topic. I also know that we're just getting towards the end of the year, and a lot of people are just over it, and that's okay. So I ask, stay with me. We're going to do some things that we saw last year. This might be a little bit easier. I don't know if you remember this or not. I'm assuming you don't, because there's no reason why I would assume that you would remember it. Hopefully it rings a bell, and today is really going to serve mostly as review of all the energy stuff that we did last year. So let's go ahead and get going. We talked a little bit about energy. We talked a lot about energy last year, and energy essentially it's defined as the ability to do work. It's also measured in joules. Little things here. Now, this definition is a bit confusing. So work has a physics definition. Work is essentially any force that is exerted over a distance. Now, if you think about that, if you are pushing something and it's going somewhere, it's essentially describing movement. So energy is defined as the ability to do work, or essentially energy is defined as the ability to move. So all energies fundamentally come down to some form of motion or another. So we know that there's potential and kinetic energy from last year. Maybe you know that thermal energy is heat energy. Thermal energy is heat energy. So if you look at the word therm, like thermometer or thermos, having to do with heat, I always say there's no such thing as cold. And that's true, because what happens is the individual air molecules are moving around. And when they bounce on your skin, it's felt as temperature. So if the air molecules are a bit sluggish and they're moving slowly, they don't have a lot of energy, you feel that as cold. And in fact, your body will then donate some of its thermal energy to the air around you. So you feel it as cold, and you're speeding up the molecules around you. That's cold air. Hot air is the exact opposite. They're colliding so much with your skin that they are actually giving some of the thermal energy to your body. And you can feel the heat entering your body. So there's no such thing as cold. It's energy leaving or entering your body. Last year, we talked about this. This is really simple. I do not want to spend a lot of time on this. Potential energy is the energy of location or position. And let's just recap. It is the energy that an object has because it has potential to move based on where it is. So if you have your calculator and it's on the floor, it has no real potential to fall. However, if you pick up the calculator and place it on your desk, you put it on the edge of your desk, it now has potential to go very fast with very little force. If you push that, if it's sitting at the edge, your calculator is sitting at the edge of your desk, and you just push it off just a little bit, it's going to go way faster than if you push off on a flat surface, because what's happening is you're releasing its potential energy. It's giving up the energy that it had based off its position to turning it into kinetic energy. So if you think about it, the higher something up is in the air, the more potential it has to fall. And again, it's the potential for movement, so therefore it's a form of energy. Potential energy is mass times gravity times height. Now, one thing I want to mention about this is that when you use this equation, energy doesn't really have a direction. Changes in energy do, but energy itself doesn't have a direction. So we are not going to use the negative for 9.8 when we use the energy. We're just going to keep it a positive 9.8 for our energy here. So any object that is above ground has potential energy. So the rock sitting at the edge of the cliff, it's on the ground, right? Like, well, let's think about it like this. It's touching a surface, but it's not like what we would call like at sea level. It has the ability to fall further down. So when we say an object that is above the ground, when I say ground, I mean the absolute like floor. So what do I mean by that? It's a matter of perspective. So we'll call ground the flat earth, the flat part of the earth. So if you're in your house, and let's just say you're on the second story, right? You know, there's the floor of your second story, right? But do objects on the floor of your second story of your house have zero potential energy? Well, technically no, because they are not on the ground of planet Earth, and they do have potential to fall. Like if someone cut a hole from the first floor right where your phone was, it could then fall because of the energy that it has, because it's not on the ground. And I say ground, I really probably mean center of the earth. So, that being said, potential energy is measured from the distance from the flat ground to where the object is. So this stone does have potential energy because it has the potential to fall. So objects that have the potential to fall have potential energy. So I know what people are thinking, like, well, if I dig a hole, right? If I dig a hole underneath my house, am I increasing the potential energy of my house? Well, in a way, kind of. Because what's happening is you've lowered the level of flat ground beneath your house. Your house now has potential to fall. That potential wasn't there until you gave it, until you moved all that dirt that was underneath your house. That was the work that you did to give your house a little bit more energy. Oh, excuse me. Kinetic energy. Kinetic energy is the energy of an object actually moving. This is the most logical and reasonable one. So essentially, if an object is moving, it has kinetic energy. And again, kinetic, kine, we know this prefix means movement. So there we go. This is so basic, I'm almost embarrassed that we have to talk about it. But here you go, 1/2 mv squared. We did this last year. So again, any object that is moving has kinetic energy. So only objects that are at rest or at a stop have no kinetic energy, all right? So motion, kinetic energy. The ability to fall, potential energy. There you go. So quick recap of units and values and equations. You might want to jot this down if you don't know it on a piece of paper, because we're going to be looking at these a lot. Okay, so height connects to potential energy. I said the quantity that determines potential energy is its height. Okay, so height is the factor, because honestly, within an object, the mass of an object doesn't tend to change from a second by second basis. Like if you have a rock, the mass of the rock isn't changing, but you can move it around and you can change its height with relative ease. Same thing with kinetic energy. Kinetic energy depends on velocity. Sure, mass is part of it, but if you're talking about like your car driving down the road, the mass of your car isn't really changing significantly as it's driving down a block. So its kinetic energy depends solely on the velocity primarily, or rather, the velocity is going to be the biggest factor in determining the kinetic energy for that object. So essentially, we know that there's these two types of energies. We have potential and kinetic. So it says, what is the height of a 50 kilogram steel beam that has 7,000 joules of energy while hanging at rest? Okay, now it says 7,000 joules of energy. I want to be very clear. I'm not saying it's potential or kinetic, but you understand we're talking about two types. We'll introduce a couple more later on, but right now we only have these two types of energy, potential and kinetic. So if I have 7,000 joules of energy, I'm not saying what type it is. So let's read the problem and try to figure out some more things here. So we're looking for the height. So height equals question mark. We have 50 kg. So 50 kg is obviously the mass. okay? Hanging at rest. If it's hanging at rest, the velocity is 0. So if the velocity is 0, that means the kinetic energy is 0. This goes back to how velocity and kinetic energy are connected. If velocity is 0, the kinetic energy is 0. I really need you to understand this concept. If the velocity is 0, the kinetic energy is 0. So it says, what is the height? So we're looking for the height, and then it has energy. So if this energy can't be kinetic, because we know the kinetic is 0, we know that the 7,000 must be potential. So there you go. A little bit of reasoning, a little bit of rationale. There you go. So PE equals mgh. We know the 7,000 is PE. We know the mass is 50. 9.8 h. Simple. Simple, simple, simple. So 7,000 divided by 50 divided by 9.8. All right. So when we divide that out, we have 14.3 meters is the height. Simple, easy, basic math. What is the mass of a bird that is perched at rest with a 4-meter high branch that has 80 joules of energy? Okay, this one's kind of similar. We're looking for mass. Now mass is in both PE and KE. All right, so I need to figure out what do we got. 4-meter high, so 4 meters is the height. Okay, just says that right there, and has 80 J of energy. 80 J. Okay, what type of energy? What type of energy? If it's at rest, I know the KE, I know the V is 0, the KE is 0. So because there isn't this energy, we must deduce that this is PE. And we're going to solve it out the exact same way again. That math is easy. I'm not going to show that, but I just want you to see these connections here. What is the velocity? All right, so now we're looking for the velocity. So automatically, because we're looking for the velocity, we know it's not at rest. It's a little bit different. Of a 4-kilogram bowling ball rolling on the ground, well, 4 kilograms, sorry, 4 kilograms is the mass. And we have 18 joules of energy. All right, perfect. When it says on the ground, that means the height is 0. If you're really on the ground, there's no additional potential to fall. And I know you'll be like, what if you're on the ground at the edge of a skyscraper? Don't overthink it like that. You're just on the ground, okay? On the ground, 0 height, 0 potential energy. Let's just keep it simple. We're not going to overcomplicate this today. So if the potential energy is 0, this has got to be the kinetic energy. So this is really simple. KE equals 1/2 mv squared. 18 equals 1/2 4v squared. We solve it out. V equals 3. Half 4 is 2, divide by 2, 9 equals v squared, square root that, John, 3. Okay, so what is the mass? Again, we're looking for a mass, so this could be PE or KE. We don't know yet because mass is in both. Driving on the ground, height 0, PE 0. 15 m/s, velocity, not too bad. And that means the energy here is kinetic. Don't have to say that, you just have to know it. So I can just go ahead and do math and figure this out. In case you want to know, because I know sometimes you've got a little weird about how you divide with the variable in the middle, the answer should be 2,500 kg. But for purposes of time, I'm going to keep it moving. So, total energy is just the sum of all the energies that an object has. So TE equals PE plus KE. all the energy is measured in joules. So another way of thinking about it is I could say that TE equals the potential energy is mgh plus 1/2 mv squared. And all I want you to know is that its energy depends entirely on how much of those two they have, and they can transfer back and forth. So I don't know if you remember doing the roller coaster simulation last year, where we had you had to go ahead and you had to ride the roller coaster and make it land, it get us points, and you could unlock the special roller coaster. But essentially, when this happens, when objects fall, think about it. If an object falls, it loses height. So because the total energy has to remain the same, according to the law of conservation of energy. If the height goes down, something else has to go up to counteract that so that this value doesn't change. So if the height goes down, that means the velocity goes up. So as you lose potential energy, as you lose height, you gain velocity, you gain kinetic energy. So just basic concepts from last year, conservation of energy, very important stuff. So it's what is the total energy of a 3 kilogram bird that's flying 4 meters per second while 7 meters high? So I'm just going to do the PE is mgh, 3, 9.8, 7, the KE is 1/2 mv squared, the KE 1/2 3, 4 squared. I just typed that all in my calculator. This is 205.8 joules, and then this is 24. Do that calculator, and you just add them up, and you have a total energy of 229.8 joules. Simple. Okay, what is the total energy of an 8 kilogram box at rest sitting on a 2 meter high shelf? All right, again, calculate the PE, calculate the KE. So the PE is mass, gravity, height. The KE is 1/2 the mass. Oh, boom, at rest. So in this case, the total energy is just going to be equal to the potential energy because there is no kinetic energy. So the potential energy here is 156.8. Simple. Simple, simple, simple. And you can solve for all these little things. So all I want you to do today is to get used to these equations, to get used to the concept of solving for those variables, understanding which type of energy applies to which situation, and seeing how, like, if you lose one of one type of energy, you get at the end another type of energy. So if I lose PE, I get KE. If I lose KE, I get PE. It's not created or destroyed. It is merely transferred between the two types. The law of conservation of energy says energy is not created or destroyed. It is only transferred. And we're going to get more into how that works next week. So, again, if you have any issues, please do not be afraid to reach out for help. I am here. We're going to figure this out together. Good luck.